Hi, today we are going to go over the latest large language model in the open source space that outperforms Gemini and ChatGPT and other closed source models. Um, and the best thing about this is that it's open source, so it's called Qwen. Um, its latest version is Qwen 2.5 by Alibaba Group and a bunch of researchers. I think um, it's the researchers from Microsoft. So let's go through the abstract and see uh, what new things have been introduced. So um, it's the newest version of large language models. Contains large multimodal models as well. They come in the range between 0.5 to 72 billion parameter models, and they feature dense models and mixture of expert models, um, which are just combination of several models trained on different, like set on different weights. Qwen 2 surpasses most prior open weight models, including its predecessor Qwen 1.5, exhibits competitive performance relative to proprietary models, like I said. So their best model has an 84.2 on MMLU, 37.9 on GPQA, and 64.6 on Human Evalve, and 89.5 on GSM 8K, and 82.4 on BBH as a base language model. So these are several benchmark tests that are used for ranking the performance of the large language models. You can read more about them later. I might even make a video on that. And like I said, these models are open source, available on Hugging Face and on GitHub. I mean, some examples are available on GitHub. Let's go to the paper. So again, it starts with ChatGPT came along, that brought some enthusiasm for large language models, that has escalated globally, and release of Llama series, which was one of the first high performance and first series of large language models that sort of outperformed ChatGPT, which is a closed source model. I think ChatGPT was the only one that was around that time. It's really like on the level they were on. Anthropic eventually has managed to catch up to ChatGPT's performance with their Opus 3 Claude 3 model. But yeah, so Llama sort of all started. Like I said, they had GPT level local LLMs. Then Claude and GPT 4.0 have updated their models. Now they are on the top. This performance is well regarded for its human evaluations. So this platform, Chatbot Arena, is basically a platform where humans evaluate the performance of LLMs. Moreover, Llama 3, I think Llama 3.2 is available now, and that sort of has become the state of the art. I think it sort of outperforms ChatGPT, even ChatGPT on some levels. And yeah, so there are a bunch of open source models now. Over the recent months, we have, like, the authors have successfully introduced Qwen series. So they came up with Qwen, then Qwen 1.5, now they are out with Qwen 2. Yeah, and this is sort of what they're introducing in this paper. Again, Qwen is a series of LLM grounded in transformer architecture. If you are not familiar with the transformer architecture, I recommend checking out the paper called "Attention Is All You Need" by Ashish Vaswani, um, who sort of came up with the architecture, and now it's used everywhere. Um, the model series encompasses foundational models as well as multimodal models. I think that's what it says here. Now they have several variations of those models. You can check out the paper later to see what sort of models that they have. All models were pre-trained on high quality and large scale data set. So this means that they are saying that they vetted the quality of data either manually or through some automated processes where they ensured that the quality of data was high quality. Now this is different because I remember that the first version of ChatGPT did not have data sets that were very high quality, and I think Mistral uh, were the people who came up with a way to make smaller large language models work better than the larger ones, or at least at the same performance or near performance, just by ensuring that they had higher quality of data. Um, I think um, I think the paper that introduced sort of that concept was "Books Are All You Need," something like that, where they fed very high quality data to their large language models, which was relatively very smaller in size. I think 2.5 billion parameters, and that still outperformed. Uh, I think 70 billion or maybe 100 billion ChatGPT 4 model. I think ChatGPT 4 has 100 billion. GPT 4 has 100 billion parameters. So I think, yeah, not outperformed, but I think the performance was relatively similar. I could be wrong, so don't quote me on that. Um, so they have conducted a thorough evaluation alongside of selection of base models, and it outperforms, like I said in the start, and the abstract said that it outperforms several open source as well as closed models, proprietary models. Here are the models, and here are the benchmarks where it outperforms several models. So you can look it up. The paper for this is just like it's titled Qwen 2 Technical Report, so it should be easy to find. Yeah. Now let's look at the model and the tokenizer. So this section introduces tokenizer and the model design for Qwen 2. We detail the model architecture and configurations of different model sizes. Tokenizer. Following Qwen, we employ an identical token based on byte level byte pair encoding. Notably, this tokenizer exhibits high quality encoding efficiency, as evidenced by its better compression rate relative to alternatives, facilitating multilingual capabilities of Qwen 2. So, upon reading this sentence, the first thing that I would go and look up is what is byte level and byte pair encoding. So this is something that I'm not familiar with, but this is something that I will go and look up later. It's fine if you don't know either, and it's good if you know. For this video, I'm not going to go and look it up, but I'd recommend that if you're watching this video, you should go do that and then come back here, as because okay, so I'll read further. So what's the use or what's the advantage of this? This gives you a better compression rate, and it facilitates multilingual capabilities. Oh, I think yeah. I think it just gives you a better compression rate, and then that gives you better multilingual capacities. Um, Models of all sizes employ a common vocabulary consisting of 1,51,643 regular tokens and 3 control tokens. For more information, you can refer to this paper. It should be noted that, owing to considerations in distributed training, the effective size of embeddings is larger. Okay, so it has 1,51,643 regular tokens. I think normal large language model has almost similar amount of vocabulary. I think I could be wrong. I think I read somewhere that it's in millions now, but given byte level and byte pair encodings, I think 1,51,000 is a small number, but I could be wrong. So I'll have to like look at more papers to know what's the standard now. It should be noted that okay, relative size of yeah, so the embeddings are larger. Okay, and it has 3 control tokens. I have no idea what control tokens are. But yeah, tokens are um, basically the smallest versions of combinations of words or combinations of 2 variables, or it could be even 1 variable. Uh, so basically, a token is the smallest unit possible, and a collection of token is called a vocabulary. So let's say if you want to write the word regular, so this word can be distributed or divided into several tokens. If you are dividing it into 2 tokens, it would be smart to divide it as reg and euler, because reg is the prefix for a lot of words. You can write regex or um, reg, regent, regent. You can make words from that. You can also use re and then make the second word euler. So re is also a good um, preface for sorry, what's the word? Yeah, the first word for yeah for a lot of words. Um, I hope that's clear. Yeah. Let's move on to the model architecture. So the Qwen 2 series fundamentally constitutes large language models based on transformer architecture featuring self-attention with causal mask. So okay, uh, so based on the citation, this is something that a normal transform architecture does. So self-attention or the attention mechanism using causal masks is a regular transform architecture. If you want to learn more, you should definitely go and read the paper. Attention is all you need. But for now, we'll just move on. Specifically, this series encompasses dense language models of 4 scales and a mixture of expert model. So again, a dense language model is maybe like a model that is literally dense, and then a mixture of experts is basically a combination of those models. But yeah, um, I think we should go and look up what dense model is. So dense model in LLMs. So in context of large language models, a dense model refers to model architecture where all parameters are activated during processing of input data. Okay, I think that is evident, and that basically it's a complete model, and a mixture of expert is a example. where only certain experts are activated based on their inputs. Okay, so I think they are pretty self-explanatory. Explanatory. Tory. Okay. So the architecture dense models comprise of transformers, like we read. Then we have group query attention. We adopt group query attention instead of conventional multi-head attention. Um, so this is something that's different in Qwen models. It's called group query attention. They also use something called dual chunk attention with yarn. To expand the context window of Qwen 2, we use dual chunk attention, which segments long sequences into chunks of manageable lengths. Okay, so it breaks down long sentences into smaller sentences, or not even sentences, smaller set of words. If the input can be handled in a chunk, dual chunk attention produces the same result as the original attention. Otherwise, DCA facilitates effective capture of relative positional information between tokens and across chunks, thereby improving long context performance. Moreover, we also employ yarn to rescale the attention weights for better length extrapolation. So, like, um, I think at this point we should also start making some notes. So, okay. When 2.5 summary, right? Let's make this a summary in this thing. So first thing it has is multi group query attention. The advantage of having group query attention was that it optimizes KV cache usage during inference and enhances throughput. We can also like include some things that we have already gone through in the summary. So we can take the tokenizer 151 643 token vocabulary. What else is information that can be used to compare the performance of these models with others. So it encompasses and a mixture of experts model. I think this entire thing can be used. Yeah. Okay. Okay. Yeah. And this is also something that we can this is something that is already it's multimodal, and then we can maybe like include this introduction. Yeah, so eventually I think this is going to uh, become a sort of a technical report on large language models. um, yeah, so okay. um, so let's continue our so it also uses DCA, double chain attention. I think it was chunk. Okay, yeah, it was chunk. And what it does is so it produces better results, but dividing things into smaller chunks, uh, which is basically you can basically um, okay, yeah, so at least it performs as good as original attention if the input size is as small as the size of the chunk, or if it's bigger than the chunk, then um, it basically divides it into a set of several chunks, which are which basically have um, mappings. So yeah, it can effective capture of relative positional information between tokens and across chunks. So basically, they have sort of context of the chunks around. Thereby, it improves long context performance, and it also uses yarn to rescale attention weights for better length extrapolation. So let's see what's yarn. So um, I don't think they mean this. So what yarn does is it rescales the attention weights for better length extrapolation. Basically, it allows for long existence of longer sentences or longer context. Oh, what did I say? Yeah, it allows existence of longer context. Yet another rope extension method, which is distinct from Apache Hanoff, which uses for management. Yarn is technically developed to extend the context window of LLMs efficiently, allowing them to handle longer sequences than they were originally trained on. Here are some aspects of yarn. So yeah, yarn represents this. Oh, so it obviously gives you longer context. It uses something called rotary position embeddings to encode positional information, extending the context window. I think this is something that needs further reading. Um, um, I think this is something that we can explore in much more detail later. But for now, we'll just like we'll copy paste the information and go over it briefly. So yep, let's move on to okay. We follow Qwen with usage of SY glue for activation, rotated position and embedding, for positional embeddings, and KQV bias, which is query, key, and value bias retention, and RMS round for pre-normalization and trading stability. So these are also some methods that have been employed to um, sort of create better performance in the model. Um, okay, and now let's look at the mixture of experts model. So this was all about the dense model. Now look at the mixture of expert models. The architecture of Qwen 2 model, mixture of expert model closely mirrors that of Qwen 1.5. Um, it acts as a substitute for original feed-forward network. So that's a simple deep learning architecture. Mixture of experts. Feed-forward network consists of n individual feed-forward networks, each serving as an expert. Each token is distributed as a specific expert for computation based on probabilities assigned by the weighted network. This is basically like setting. Basically, we assign an expert based on our task, and when we come across that task, let's say like I ask you to do some mathematical problem. I ask the model to do some mathematical problem. It would basically look at basically divert the task towards the architecture or the sub-architecture of the model that is more equipped at handling those tasks. Um, at least that's what I understand from mixture of expert models, and uses sort of a soft max technique, which is basically assigning the max value based on your decision. So let's say like you have 5 or 6 options, and you would use based on your judgment um, a softmax operation to give the highest weight, that is 1, to a model, and 0 to others, based on the task, based on the relevance of the task, right? So here we have the architecture of those models. All of them have 646 token vocabulary. So I think yeah. So yeah, I mean you can look up the architecture. There's not much to explain. The key structural difference between MOE, mixture of expert, and dense model is that the MOE incorporate multiple feed-forward networks, each serving as an individual expert. Consequently, one straightforward strategy is to transition from dense architecture to a mixture of experts architecture. Um, Really, one straightforward strategy to transition from a dense architecture to a mixture of expert architecture is to set parameters for each expert equal to those of single feed-forward networks from original dense model. For example, transitioning from Mistral 7B to Mistral 8x7B involves activating one of 8 experts at a time. Differently, our model employs fine-grained experts, creating smaller scale experts while activating a greater number of experts simultaneously. So I think this is a very intelligent way to do this, for 2 reasons. Because I think if you do this, you can sort of double check your model's generations or your model's outputs. So I think they have they have better chance of being correct, and at the same time you can uh, achieve a better performance with a smaller model. Um, this is because you are double checking, and um, yeah, sort of that. So definitely our model employs fine-grained experts creating small and grade. Given total Given an equal total number of experts, parameters, and activated parameters, fine-grained experts offer a richer set of expert combinations. By leveraging these fine-grained experts, Qwen 2 MOE facilitates more diverse and dynamic expert utilization, thereby enhancing overall performance and reliability. So yeah, exactly like what I just talked about. Uh, having having two or more mixture of model expert models which are smaller uh, give better performance than using just a single mixture of expert models, even if they have the same number of parameters. mm, so yeah, um, let's look at how they are doing the expert routing part. So the design of expert routing mechanism is crucial for enhancing the performance of mixture of expert models. Recently, there has been a notable trend towards integrating both shared and routing specific experts within a MOE layer. We look at this approach as it facilitates the application of shared experts across various tasks while reserving others for selective use of specific routing scenarios. The introduction of shared and precise experts offer a more adaptable and efficient method for developing MOE routing mechanisms. So I think this and this paragraph was self-explanatory, and um, I don't think that we need to discuss more on this. So let's move on to the next one. This explains the expert initialization process. We initialize the experts in a similar way by upcycling or leveraging the weights of a dense model. In contrast, our approach emphasizes diversification among fine-grained experts to enhance model's representational breadth. Given the designated expert intermediate size HE, the number of experts N, and the original feed for intermediate size HFFN, the FFN is replicated N into um, HE, which is the size of the expert, by the original intermediate size of the larger model. This replication ensures compatibility with specified number of experts while accommodating any arbitrary expert intermediate size to promote diversity within each FFN. Copy parameters are shuffled along intermediate dimension. This guarantees that each fine-grained expert exhibits unique characteristics even across different copies. Um, so I think this is self-explanatory. If you did not understand, this basically creates number of the size of intermediate expert and number of experts by total size of layers in the larger model, number of replications. So, and basically it asks every time it um, asks the asks the small subset of expert to or sub expert or to create an output, and uh, basically those outputs are used for creation of final output. Um, Also, this process introduces additional stochasticity into expert initialization and potentially enhancing the model's capacity of exploring and training. So, mixture of expert, this model, mixture of expert, it has, I mean, all this is sort of very common technique, but let's, so they are doing is smaller experts, but using multiple experts at the same time to give a better result with similar or less number of parameters. I think this is what I understood from like reading all this. Uh, so they have a routing. Um, use shared and outer specific experts. Oh, so I think this is how they are creating those experts. Um, so they are creating, um, and then they are sort of dropping 50% of its parameters for each expert and reinitializing those weights. This sort of adds an element of stochasticity, which is basically randomness. Uh, I mean, I think this is like in this context, stochasticity means a little bit of flexibility or randomness, or maybe redistribution of probabilities. Um, let's look at its configuration. Consider 5 model sizes. Yeah, it's okay. There was a substitution local key value size per token related to Qwen 1.5, and they have not mentioned anything else or comparison with other models, but it might be somewhere. Okay. Now let's look at the data, because data is very crucial. Okay. So, wait, this is pre-training step, not the data column, but I think, yeah, data is very relevant because we need some data, right? So for the pre-training step of Qwen 2.5 or 2, our efforts were focused on refining the datasets and investigating methods to handle extended context lengths. So I think we just read a few method of handling those extended context lengths, and now let's read about refining the datasets. So for pre-training data, the pre-training of Qwen 2 models involves development of large language, high quality multilingual datasets. These datasets represent an improvement over corpora uses used in Qwen and Qwen 1.5 models, and enhancing the scale, quality, and diversity. Okay, so it says that they use a new large scale, high quality multilingual dataset, but without numbers, these things um, can't be compared to. But they claim that it's better than their previous version of models, but unless there's some quantitative comparison, we can't say how better it is or how more diverse it is. Let's look at quality enhancement techniques that they've employed. So they used a filtering algorithm that has refined with additional heuristics and model-based methods, including the use of Qwen model for filtering out low-quality data. Moreover, these models are utilized to synthesize high-quality pre-training dataset. Okay. Data expansion compared to Qwen 1.5, we have collected a significantly larger volume of high quality code, mathematical multilingual data. So, okay. So again, they said that they have improved the quality um, and come up with a way to filter out low quality data. Compared to 1.5, they have larger volumes of code, mathematics, and multilingual data, so they have sort of increased uh, the quality and the size of the data sets. I think that's the only thing I got from this. I got no specific information about this, at least yet. In context of the data, to ensure model learns distribution again of human-like learning, we conduct experiments on scaled-down models to optimize mixing of data from various sources and domains. So, learns from distribution. I mean, human-like learning. We conduct scaled-down models to optimizing the mixing of data with various sources and domains. Okay, based on these enhancements, pre-training data was expanded from 3 trillion tokens in Qwen 1.5 to 7 trillion tokens. So I think that's more than double the data. Um, Almost 2.25 times. I think. An attempt to further relax the quality threshold resulted in 12 trillion token dataset. However, the model trained on this dataset did not show a significant performance improvement over 7 trillion model. So I think this emphasizes that data quality is still a very relevant and important metric. Um, it is suspected that increase the volume of data does not necessarily benefit um, the model pre-training. Considering training costs, we opted for the use of higher quality 7 trillion token dataset for training large language models, leaving further exploration of future model iterations. Uh, okay. So small models were also trained on 7 trillion tokens. Um, okay, Qwen 2, except this was trained on 7 trillion. Qwen 2 0.5 was trained on 12 billion. Issue of expert models resulted in an additional 4 trillion tokens of pre-training in line with principle of upcycling. Similar to previous Qwen models, high quality multitask instruction is integrated in Qwen 2 pre-training process in context to enhance in context learning and information following abilities. So this is an important change, right? Not change, but addition. Um, this is what I uh, got from reading the section. Now let's look at long context training. To enhance the long context capability of Qwen 2, we augmented the context length from 4096 to 32,000 tokens during the concluding phase of pre-training. I think this has something to do with the CPA, DCA, double chain attention technique that we just read about. But let's look at if they provide any further explanation to this. Expansion was complemented by introduction of significantly increased volume of high quality and lengthy data. In conjunction with this enhancement, we modifies the base frequency of rope from 10,000 to 1 million for long context scenario. We leverage models length extrapolation potential. We adopted yarn mechanism and double chunk attention. These strategies enable the models to produce. These strategies enabled to process over 131,072 tokens while maintaining high performance, as evidenced by minimal perplexity degradation and preliminary experiments. Um, so basically, it was good. Now for post training, um, enhancing proficiency across broad spectrum of domains, during coding, mathematical, logical reasoning, where it ensures the generation of model is in harmony with human values, making it helpful and honest and harmless. Unlike traditional models, wait. This is important. It ensures that the generation of models is in harmony with human values and makes it helpful, honest, and harmless. So I think this means that they have put safeguards on their models, but I have not read any specific mention of them. Uh, but let's keep reading and figure it out, right? Um, this process is proficiency in okay. Unlike traditional methods that heavily rely on extensive human supervision for our supervision, our approaches focuses on scalable alignment with minimal human annotation. Uh, okay. So we will be investigating methods to acquire high quality demonstration and preference data for supervised fine tuning and reinforcement learning from human feedback, aiming to minimize the need for human labeling while maximizing the quality and reliability of data. Investigate methods to acquire high quality demonstration and preference data. Okay. Post-training data. The post-training data primarily consists of two components: demonstration data and preference data. Where xi is the represents the instruction, yi represents the satisfactory response, and yi plus and yi minus are two responses to xi, with yi plus being the preferred choice over yi minus. The set is utilized in SFT, whereas P is employed in RLFH. Okay. So post-training data consists of two components: demonstration data. Demonstration data has xi, which is instruction, and this is the response, and P preference data, where you give the instruction and two responses, and which one is preferable. So set D is utilized in XFT, whereas P is employed in RLFH. Are they using both of them? Methods to acquire preference. Okay, so they are using SFT and RLFH both. RLHF both. So is this just for generating their datas? Post training, okay. Methods to acquire high demonstration preference data from. Okay. These are the two methods that they have employed. They have made automated methods of human annotation without human intervention for these two methods, and this is how those two methods are sort of made. Okay. So how does this work? So the construction of training data entails two-step process: collaborative data annotation and automated data synthesis. First, we extract data ontology from large-scale instruction corpora, leading to a broad and diverse set of high-quality instructions. These instructions are systematically enhanced to incorporate greater complexity. Through human annotation, we obtain a target response yi and their positive and negative counterparts. Subsequently, a variety of automated alignment strategies are employed to synthesize a substantial volume of artificially annotated data across domains of code, mathematics, instruction following, creation, role playing, and safety. So basically, they are automating uh, alignment to synthesize artificially annotated data sets. And to annotate this, humans are used. So target response and their positive or negative counterparts. So this target response is used for supervised fine tuning, and the negative and the positive counterparts are used for RLFH, RLHF uh, training. Uh, okay, now here's several methods of annotation, data annotation that they have used, and several methods of uh, data synthesis that they have used, uh, which I'm not going to go over because these are strategies that you can read. These are not very something unique to this. These are, I think, used everywhere now. Um, I'll just go over it briefly. So they use automatic ontology extraction, instruction selection, instruction evolution, human annotation. Instruction evolution is basically it's a self-evolution strategy where you prompt the large language models to add constraints and requirements for existing instructions. Human annotation is where human is intervening, automated data synthesis, you do rejection sampling. Rejection sampling is something you can read about in the papers later. Feedback is uh, again a technique that's used. You can read about it in this paper. Data repurposing, again, it's a straightforward technique. You can just look it up and find out what it means. So if you're looking at supervised, so let's look at the post-training supervised fine-tuning. So we have assembled an extensive instruction data set featuring more than 500,000 examples that cover skills such as instruction following, coding, mathematics, logical reasoning, role-playing, multilingualism, and safety. Our model was fine-tuned for two epochs where it's okay. So the model was like fine-tuned for only two epochs. SFT. Using 32,768 tokens to optimize learning. The learning rate was very small, and it also decayed. And then there was some weight decay of 0.1, and gradients were clipped. So they have also used gradient clipping and weight decay. Okay. And now let's look at RLHF process or part or process. Yeah. Training regime for RLHF comprises of two sequential stages: offline and online training. In offline training stage, we use pre-compiled preference data set P, which contains instruction and then a positive preferred response and an unpreferred or a negative not preferred response. And we try to maximize the difference in likelihood between yi plus and yi minus with DPO, direct preference optimization. In the online learning stage, the model iteratively refines its performance in real time, leveraging reward models models for intermediate feedback. Specifically, we sample multiple responses from current policy model and reward model, selects the most and least preferred responses, forming a preference pair that are used for DPO in each episode. Moreover, we employ online merging optimizer to mitigate the alignment tax and performance degradation association with aligning model generation with human preferences. So basically, we use a method called direct preference optimization, and we use the reward mechanism for generating the most preferred responses. Okay, I think these are several benchmark evaluations of the model. So you can look it up if you want, but it performs very well on comparison. So with the existing open source and large language models. So with that, I'd like to conclude the reading session. I'd like to do more of these in the future. Please comment and let me know if you like this and would like me to do more of these. But yeah, before going, let's read through this. So okay, so let's look at the most important aspect. I mean, it's an important aspect of large language models, which is safety and responsibility. So let's look at performance of models in safety evaluation. We compare Qwen 2 with GPT-4 and Mistral, and having a lower score is better. So basically, basically instructions are injected with harmful prompts, and they compare the risk. So and the lower risk is better here. So I think Qwen is performing significantly better than its competitors. This is, I think, is percentage values. So as you can see, Qwen is performing a lot better. So basically, it is much more safer or much more less likely to generate harmful responses, which is a good thing. So that is also going very well, in a good direction. And let's look at the conclusion. So conclusion says that we presented. So it's a small summary of everything that we just discussed in the paper. If you like this video, please throw in a like. Like I said, if you are interested in having me conduct more reading sessions like this, please let me know in the comments, or whatever way you wanna.